Let's look at some examples of combining inverse trig and regular trig functions. I often call them forward trig functions. First, a real quick context setting. Remember what we're doing here is we're doing the backwards version of what we've been doing before. We would have an angle t. This gives it to us in degrees, although we usually think of it in radians. And then the cosine is the x, the y is the height or the sine. And now we're doing it backwards. We're saying, suppose I'm looking for, I know that the height of the point, let's say, is 1/2. I want to find the mystery t. Okay, well, let's see. It's not quite right. It's pretty close. To get a half for the sine, we actually happen to know that angle. We know that a 30-degree angle, or pi/6, will work. I have that on another picture right here. I know that if the y's coordinates is 1/2, I know this angle here has got to be pi/6, and I put that angle up here. And so for some of these guys, it's a matter of just doing our little mini quizzes in reverse. But more generally, it's going to be a little more interesting for other points on the unit circle. In the other graph, I've got something that's a variable point, and I can go anywhere. And I can think, okay, what if the height is 0.38? What's the angle corresponding to that? Well, it looks like 22.5 degrees, roughly, is the angle. Often we're going to need to use the calculator, but there's some things we can do without the calculator, and that's what this is about. So let's look at some interesting combinations of combining forward and regular trig functions, or rather inverse and regular trig functions. So every one of these is of the form, I'm matching a trig function with its inverse. Soon we're going to match a trig function with a different trig function's inverse, and that's actually very cool, and it's actually in disguise something we've done before. These guys are fairly simple, but it gets at some of the subtleties about this subject. Morally speaking, if you combine a function with its inverse in either direction, like this or like this, you should just, nothing should happen, really, because I'm supposed to be going forward and backwards, and I should just get what I start out with. That's not always going to happen, though. Let's look at it here. Inverse sine of 1/2, that's what I was just doing up here. The inverse sine of 1/2 in radians is pi/6. We happen to know that answer, and sine of pi/6 is 1/2. Well, did we really have to do that? Well, let's see. We're looking for this. What was special about pi/6 is this is the angle whose sine is 1/2, and then I took the sine of it. So here's what what it comes down to. I am thinking of an angle whose sine is 1/2. That's what this means. The angle whose sine is 1/2, or really the simplest angle whose sine is 1/2. And we'll get to that soon. Okay. And then I ask you. I don't ask you what the angle is. I actually didn't care about the pi/6 here. I say, what is its sine? Like, I'm thinking of the person who is the king of Sweden. What is he king of? You don't need to know who the king of Sweden is to know that it's Sweden. The answer is Sweden. Okay, I'm looking for an angle whose sine is 1/2. What is its sine? It's obviously going to be 1/2. Okay, so these problems tend to be quite simple. I'll show you one subtlety, though. But let's see. Cosine of inverse cosine of 0.6. Well, let's see. If I really wanted to think about what the intermediate stages were, I'd find this point with 0.6. Turns out to be about a weird angle, like 53 degrees. But I don't need to know that. I just need to know that if I'm thinking of this angle, and the reason I'm thinking about it is that its cosine was 0.6, that's what this is. This is this mystery angle. And then I don't ask you for the angle, I just ask you for its cosine. Boom, it's 0.6. Okay. Similarly, the tan of inverse tan of -5. Well, where would that be on the circle? If we needed to know more about it, that's something where the slope, oh, I forgot to put the tangent here, but we can sort of rough it. It's supposed to be a major downward slope and about a 5-to-1 ratio. That's about right. So this is about 5 times bigger than this, so the ratio would be about 5, but I forgot to put it on. Okay, so that's going to be about a 77.6 degree angle, but it's going to be negative. Well, we could convert to radians, or we could use the calculator in radians, but none of that's necessary, because I don't ask for what this angle is. I don't have to compute it in stages. I have to look at the idea. Here's an angle whose tangent is -5. What is its tangent? Equal -5. So these guys are almost always quite easy. Forward of inverse. Forward function of the same inverse function. Here's a tricky one, though. I'm thinking of an angle whose cosine is 3. What is its cosine? Well, it seems like the answer would be 3, just in analogy with the other ones. But let's think about it. I'm thinking of an angle whose cosine is 3. I'm thinking of an angle, or I claim to be thinking of an angle, on the unit circle that is 3 units to the right of the origin. No way, I'm lying. There is no such thing. Okay, this just does not exist. Or let's say it's undefined. Okay, because the middle is undefined. That's something where you have to be a little careful about. That just doesn't make any sense. So it's not absolutely always you can just cross these out and say, oh, done. But usually you can. Okay, now what about going the other direction? Here's one that's almost as easy. I look at pi over 6. Let's go to our standard angles picture. I look at pi over 6, and I find its sine. That's 1/2. And then I look for the mystery angle whose sine is 1/2. Well, wait a minute. That's the angle I started with, because that was what's interesting about this. I had an angle, pi over 6, whose sine is 1/2. And then I say, what's the mystery angle that would give me that? Well, I just had it. That's why I did this. Okay. So this is equal to pi over 6. Okay. So here it's I have calculated the intermediate stages. I have calculated the height of angle pi over 6 to be 1/2. Can you possibly imagine an angle whose height is 1/2? Because that's what the outer layer does. Here's 1/2 is the height of angle, pi over 6. And then this thing says, what's the mystery angle that could give me that height? Well, that's what I started with. Okay. And so that's not too bad. Again, the inverse and the forward function cancel out. But this is where it gets it more interesting. Inverse sine of 5 pi over 6. Okay. So let me amend this. So it's really not quite this. It's really, can you give me the simplest angle whose height is 1/2? It's still pi over 6, because that is absolutely the simplest angle whose height is 1/2. But here, it would not be true that 5 pi over 6 would be right. Let's see. 5 pi over 6 is over here. Its sine is 1/2. And it's true that n angle that would give me that height is 5 pi over 6 itself. But it's not the simplest one, because over here is a simpler point with the same height. Okay. And so this is the simplest point with the same height. I like to call this, well, let's just write down the answer. It's equal to, sorry, pi over 6. Because that's the simplest point with the same sign. So I call this the simplest cousin of 5 pi over 6. Now it's a little bit rough terminology, because as far as sine is concerned, okay, I like to call it the simplest cousin. It doesn't give you back the same angle. It gives you back the simplest angle that has the same height. Okay, so that's a better way. That's a more precise way to say it. In this case, it's the simplest angle which has the same height. And here I have to make sure what we know what simplest means. Simplest for the inverse sine function means in the standard range. This is where it connects to the graphing stuff. We found out that minus pi over 2 to pi over 2 is the right range of those guys. And so that means it's going to be in minus pi over 2 to pi over 2. And I guess I should have made that all math brackets. Okay. So that's making it more precise. So mainly the thing is to remember that these issues are out there. Then you do have to remember exactly what the precise definitions are. Okay. So this is what I call the simplest cousin phenomenon. What about this? Inverse cosine of cosine minus pi over 3. Well, this is where it gets tricky again, because cosine has a different notion of what cousin and simple mean. So I take cosine of minus pi over 3. Okay, that's this angle down here. The cosine is 1/2. And then I want the inverse cosine. That's the simplest angle that also has that x-coordinate. Well, here's another angle that has the same x-coordinate, pi over 3. And that really is simpler. It's in the first quadrant. There's no negative. And so that really is going to be the right answer. It's going to be pi over 3, not minus pi over 3. You can't just cross these out, unfortunately. All comes back to this amputation issue that we talked about with the graphs, that these functions don't really deserve to have inverses. And so these quote inverses that we create for them don't have all the nice properties that inverses should have. And so here, this is the simplest angle which has the same x-coordinate. And here, simplest means in 0 to pi. Okay, so all the only answers you should ever get for an inverse cosine are 0 to pi, and the only answers for an inverse sine should only ever be minus pi over 2 to pi over 2. Okay, now here's the trickiest one. Inverse sine of 2. Now I don't mean 2 degrees. If I don't put a degree symbol, I never mean degrees. I mean 2 radians. That doesn't have a pi in it, but that does not mean it can't be radians. Very important. You get used to all these pi's as our simple angles. 2 radians means mark off this distance, which is 1 radius, then go 1, 2 of those, and somewhere around here is that point. Somewhere like right around. Oh, I've got these tiny little points. Sorry, right around here is that 2 radians. It's a little less than 2 pi over 3 because pi is a little bit bigger than 3. Okay, so that has a perfectly well-defined sine. It has a certain height. And if that were in the magic set of simple angles, if 2 were between minus pi over 2 and pi over 2, this would be easy. It would just be 2. You just get back to the angle you started with, 2 radians. But it's not. So what we need to do is we need to figure out, okay, it looks like that's going to be about the same height, I'm going to eyeball it even though I shouldn't, as right over here. And I need to know, what is this angle? Let me put in a segment. What is this angle in here? Because that's the simplest angle that has the same height as, let me put in here, as this angle. This was the 2 radians, and then this is its simplest cousin. This is where some of those identities come in. Here, we have to remember that we know how to flip an angle, even if it's a weird angle, even if it's totally random or even a variable, we know how to flip an angle over the y-axis. It's taking pi minus. Pi minus gives you exactly how much is left over in here. If you have half of a pizza, that's pi radians of pizza, and you take out this much, it gives you this angle. Well, guess what? That angle is exactly the angle over here that we were looking for. Okay, and so we get that it's the simplest cousin, which is the flipped version, which is pi minus 2. That's definitely trickier, but it's the same principle. It's the simplest cousin of 2 radians.